Hello again. This is Math 2233 coming to you from the College of DuPage. The title of this lecture is Partial Derivatives, and as always, I encourage you to be an active learner as you watch this video. On a hot day, extreme humidity makes us think the temperature is higher than it really is, whereas in very dry air, we perceive the temperature to be lower than the thermometer indicates. The National Weather Service has devised a heat index, also called the temperature humidity index, to describe the combined effects of temperature and humidity. The heat index is perceived air temperature when the actual temperature is capital T and the relative humidity is capital H. So I, the index, is a function of H and T, and we write I is equal to F of T and H. And the following table of values is an excerpt from a table that's compiled and maintained by the National Weather Service. And so you can see this picture. If we concentrate on the highlighted column of the table, let's go down here. We're assuming that the relative humidity is 70, and we're looking at how does the perceived temperature change as the temperature goes from 90 to 100. So these are the changes for that fixed value. So let's write G of T equal F of T comma 70. We fixed the 70. Then G of T describes how the heat index increases as the actual temperature T increases when the relative humidity is 70%. Now the derivative of G when T equal 96 degrees Fahrenheit is the rate of change of the index with respect to T when T is equal to 96. So you see here's what we have. G prime evaluated 96 this is the limit of the slope of the tangent line. We take the limit as h goes to 0. G of 96 plus h minus G of 96 over h. And that's equal to this limit. And now we're replacing G with F, but now we see that F has 70 fixed. So we can approximate G prime of 96 using the value in the table, because we can take h being 2 and h being minus 2. So you see if we go minus 2, we go from 96 down to 94. If we go plus 2, we go up to 98, and we get these numbers. So we can calculate these values of the secant lines, and we'll get 4 and 3.5 respectively. Now if we average these two values, we see that G prime of 96 is approximately 3.75. That means that when the actual temperature is 96 degrees and the relative humidity is 70, the apparent temperature heat index rises by about 3.75 degrees Fahrenheit for every degree the actual temperature rises. Now let's take a look at the highlighted row in the same table. So here is the highlighted row. And again, that's a fixed temperature of 96. So the numbers in the row are the values of the function capital G of H equal F of 96 comma H, which describe how the heat index increases as the relative humidity H increases when the actual temperature is 96. The derivative of this function is the rate of change with respect to H when H is equal to 70. And so it's G prime of 70 is equal to the limit as H goes to 0 of capital G, 70 plus H minus G of 70 all over H, and then I change that to my function F, and see I'm changing the second variable, not the first. And if we take H to be 5 and minus 5, what we can see is that we're looking at this value when I'm at 65 and this value when I'm at 75. And so I evaluate that and I get 1 and I get 0.8, and that means that the derivative, if I take the average, is approximately 0.9. This says that when the temperature is 96 degrees Fahrenheit and the relative humidity is 70%, the heat index rises about almost a degree. It's 0.9 degrees Fahrenheit for every percent that the relative humidity rises. Now, in general, if f is a function of two variables, x and y, suppose we let only x vary while keeping y fixed, say y is equal to b, where b is some constant, then we're really considering a function of a single variable, namely g of x is equal to f of x comma b, where b is the constant. If g has a derivative at a, then we call it the partial derivative of f with respect to x at the point a comma b, and denote this by f sub x of ab. Thus, f sub x at ab is equal to g prime at a, where g of x is equal to f of xb. And if we look at the definition of derivative, we see that g prime of a is equal to the limit as h goes to 0 of g of a plus h minus g of a all over h. So our equation up here becomes, so f sub x at ab is the limit as h goes to 0 of f of a plus h comma b minus f of ab all over h. Similarly, the partial derivative of f with respect to y at ab, denoted by f sub y of ab, is obtained by keeping x fixed. X is fixed in this concept discussion at x equal a, and finding the ordinary derivative of this function, capital G of y equal f of a y, but evaluating it at b. That is, f sub y at ab is equal to the limit as h goes to 0 of f of a comma b plus h minus f of a b divided by h. With this notation for partial derivatives, we can return to our original example and write the rates of change of the heat index with respect to the actual temperature, T, and the relative humidity when T is 96 and H is 70% as F sub T of 96,70 was approximately 3.75, and F sub H 96,70 was approximately 0.9. Now, if we let that point AB vary in the equations that we talked about, these become, in the same way they did with single variable calculus, functions of two variables. So here is a definition for you. If f is a function of two variables, its partial derivatives are the functions f sub x and f sub y, defined by f sub x is equal to this limit, and f sub y is equal to this limit. Now, there are many notations for these partial derivatives. Sometimes we write f sub x, showing us x and y. Sometimes we just do f sub x. Sometimes we use these curly brackets to indicate that we have partials. So this is a partial of f with respect to x, or the partial of f of xy with respect to x. And sometimes if we call this z equals f of xy, we say this is a partial of z with respect to x. Notice again the curly brackets. Similarly for f sub y. Now, to compute partial derivatives, all we have to do is remember that the partial derivative with respect to x is just the ordinary derivative of the function g of a single variable that we get by keeping y fixed. So we have the following rule. To find the derivative partial with respect to x, we just say pretend y is a constant and use all my rules that I know and learned in Calc 1 to differentiate f of xy with respect to x. And similarly for y, we regard x as a constant and differentiate f of xy with respect to y. Let's do an example. So suppose z equals f of xy equal y squared x plus y e to the x minus x natural logarithm of y. So this is our z. If I take the derivative with respect to x, I assume that y is a constant. So I'm only taking the derivative of x. So this is the constant y squared times x plus y times e to the x plus the constant ln y times x. So when I go through and take the derivative this is just like 5x, so I'm just taking the derivative with respect to x. I get y squared. When I take the derivative of this, y is a constant, so I take the derivative of e to the x, which is e to the x. And here I have the constant ln y times x, so the derivative with respect to x is just minus ln y. So this is the partial with respect to x. If I take the partial with respect to y, I assume x is a constant. So this is x, the constant, times the variable y squared. This is the constant e to the x times the variable y. And this is the constant x times the function of y, ln y. And now I'm taking the derivative with respect to y. So f sub y is equal to. So the x just sits there, but I take the derivative of y squared, which is 2y, plus the e to the x just sits there. It's a constant, but I take the derivative of y with respect to y. I just get e to the x. And here the x just sits there, but the derivative of the natural logarithm of y with respect to y is 1 over y. So f sub y is equal to 2yx plus e to the x minus x over y. Now here's a problem for you to do. And what you want to do is find the partial with respect to x at the point 2, 1, and the partial of y with respect to the partial of f with respect to y at the point 2, 1. Now these answers are going to be numbers, and this is actually more the kind of problem I probably would ask you on an assessment. You know what to do. Let's see how you did. Okay, when you take the partial with respect to x, you get 3x squared plus 2x y cubed. So when I substitute in 2 for x and 1 for y, I do the calculation, I get a numerical value of 16. If I hold x constant and differentiate with respect to y, I get this, 3x squared y squared minus 4y. And when I plug in again x to be 2 and y to be 1, I get the constant 8. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.